joint collaboration between New York University, New York and New York University in Abu Dhabi. And the objective here is to guarantee ensure safety for robotic systems. In special, we want to guarantee collision avoidance. And a pretty popular approach is using control variable function, right? So here we're going to use control variable functions, and in order to do so, we have to go through 3 steps. First, we need to define the safe set. Then we need to synthesize the CBF function, here denoted by H. And once you have the CBF function, you have to implement it using an inequality that you're going to insert into an optimization problem. And once you solve this optimization problem, you get a safe control input. In this work, we're going to focus on the CBF synthesis, right? The second step here. Okay, so to synthesize the CBF, you're going to use the scaling metric, which is a pretty interesting distance-like metric that works like this. So you have 2 objects, like you have here a box and a cylinder. You're going to scale each one of them using exactly the same scaling factor until they touch each other, until there is a contact point. When there is a contact point, you get this common scaling factor as the scaling metric of the objects, right? With this, we can see that when the scaling metric is greater than 1, you'll have to span the objects to collide, so therefore the objects weren't colliding in the first place, right? So no collision. Whereas if you have a scaling factor that is less than or equal to 1, that means that the original objects were colliding already. And furthermore, the more overlap you had in the first place, the lower is this scaling metric. So it has this pretty interesting property that is valid, that is defined even when you have overlap. So it measures how much you are overlapping. And also, in order to compute this scaling metric, we can set up an optimization problem that I'm going to go back to it pretty soon. And another interesting property is that you can compute the derivative of this scaling metric straight from the KKT conditions of this optimization problem, which is pretty convenient because we are going to need the derivative in order to implement the CBF function. With that said, we are going to define our CBF function H as this scaling factor alpha minus a margin that should be greater than 1. So, if we guarantee that the CBF function is greater than or equal to 0, we guarantee that the scaling metric is greater than 1, so therefore the 2 objects are not going to collide. Okay, so we would like to provide some formal guarantees for this scaling metric, right? And the first one that we provide in the paper is about continuity. So we can ensure that this alpha, and therefore the CBF function as well, because they are essentially the same, save a margin, is a continuous function as a function of the pose of both objects. Of course, I don't have time to go through everything here, so I'm going to go very quickly in some key points. In order to establish continuity, we need to study this function gamma here that maps the poses of the 2 objects into a set, which is essentially the constraint set of the optimization problem you have to solve in order to obtain the scaling factor, right? And we can prove that this function that maps into a set has the property of upper M continuity and lower M continuity, which are essentially continuity but for sets, right? Because the codomain of this function is a set. Once we prove that, we can use Burge maximum theorem to establish that indeed this scaling factor, and therefore the CBF function, is a continuous function of the poses of both objects A and B. Okay, so this first property that we can guarantee continuity, but we would like to guarantee more than that. Because in order to implement the CBF inequality, we need to compute the derivative of the CBF function, and therefore the derivative of the scaling metric. So we also show some results concerning differentiability, which is stronger than continuity. But to do so, we need to go back to the optimization problem. To the left here, you see the original optimization problem that I showed. And we can see that it is described using a set language. So P should be inside the set PA alpha, which is essentially the scaled version of the original set A. And the same should hold true for the set B as well. But this is in set notation, right? So P should be inside the set, and P should be also inside the other set. But in order to provide the theoretical results, and also to implement this, to solve this optimization problem in a solver, we need to transform from this set language to the language of functions, to the language of inequalities. So for PA alpha and PB alpha, these 2 constraints, we can write down these functions FA and FB, and implement exactly the same constraints, but using inequality instead of using set membership. Okay, so this is a case-by-case basis. So for each different type of objects that you want to implement, you have different functions FA and FB, right? So you have one for cylinders, one for spheres, and so on and so forth. Once we do that, in order to ensure differentiability, we need some conditions. The first one is a kind of regularity condition. Essentially, it should hold true that the gradient of these functions FA and FB shouldn't vanish at the same time, which is a kind of a weak condition. So to give an example, when the two objects are ellipsoid, that would mean that they can't have their centers being exactly the same point, which is pretty reasonable, right? So it's a kind of a weak condition. But we also need some additional conditions in order to guarantee differentiability. So from FA and FB, we derive the function GA and GB. They are related to each other. And we need some conditions for those as well. We need that they are continuous, differentiable, and twice differentiable. And we need a pretty important condition, which is that GA and GB are strongly convex functions on P, on the position P. And if you have all these conditions, including the regularity condition that I mentioned just before, we can indeed guarantee that alpha, the scaling metric, and therefore the CBF as well, is a differentiable function of the poses of two objects, right? As I say, I have to go through very fast, but in case there's some questions, I can try to answer, of course. All right, so other than the theoretical results, we also provided some experiments, some experimental results. Here. So we have this robot, the Franka-Emika. So we model the robot using some convex shapes. So we have cylinders, spheres, capsules, and ellipsoids. And the task here is to achieve a given pose while avoiding these virtual obstacles. And since all the primitives and all the obstacles are convex functions, we can solve the optimization problem to compute the scaling factor and therefore the CBF very quickly because it's a convex optimization problem, right? So it can be done very, 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 very quickly. There's another one as well, which is similar, but this time you have three cubes, and again, the task is to reach a target pose while avoiding collision with the environment, and it was successful in doing so. All right, to verify that indeed it was safe, there were no collisions, we need to check the CBF functions, right? So if they are above 0, that means that no collision occurred. So for each object in the environment, we have a distinct CBF function, so we need to check each one of those, right? So you have here the simulation experiment for the same scenario. And for example, in the simulation here, in the upper left, you can see the 4 CBF functions as a function of the time. And you can see that all of them are above 0, which means that it was safe as expected. And the same holds true for all the other examples that we see here. So indeed, by verifying the CBF functions, everything was safe. Furthermore, we mentioned some theoretical results about differentiability, right? So what we did here is that we require some conditions for differentiability, but we wanted to see what would happen if we didn't have these conditions, right? So in both cases here, we have 2 rows for 2 different experiments. And we are showing the derivative of the scaling metric, therefore of the CBF function, because it is the same. The partial derivatives with respect to the poses of each one of the objects, so x, I, z, and the 4 entries of the quaternion, for each one of the objects that compose the robot, right? So an object for link 3, an object for link 4, so on and so forth. So in the top row, we can see that everything was continuous. So even though we didn't have the theoretical guarantee that we required, even then it was continuous, right? And in the bottom row, it was almost always continuous except for a jump here in link 3, so it's the second row, first column, in which we see a single jump. So when it is not continuous differentiable, it seems that it only has a very few points of discontinuity of the derivative, right? This shows us that there is a way to extend recent results to stronger conditions than the one that we have right now. We can extend these theoretical results to other shapes other than the ones we considered in this work. Okay, so in conclusion, we presented a systematic and computationally simple approach, because as I say, that if everything is convex, very quick to compute. CBF based on the scaling metric. We showed some theoretical guarantees related to continuity and differentiability under some conditions, and we also experimentally demonstrated these results in a real world. Since this work was concluded, we were able, our team, to extend these results. So we have two papers here in which you can see more general versions of the results that we have in this book. And yes, this is it. Thank you very much.
So the safety guarantees of CBFs can fail if it's not always possible to find a use satisfying a constraint, like if the CHDX should be zero at some points. Is there a way to verify whether that happens?
Yeah, in this case, because it depends on the dynamics as well, right? Which dynamics we assume. Because here we focus on the function itself. But in this experiment, we assume that we can control the velocity. So therefore, the dynamics is Q dot equals to U, in which Q is the configuration. In that case, it's always feasible as long as we are inside the safe set, because stopping is always a possibility, right? You can just set 0 and it's fine. So for this particular case, you can always ensure feasibility. For more general system, for more general dynamics, it's case-by-case basis. But here in this work, we focus on the function itself.
Our time, thank you.